me to today a special occurrence of CME Linear Algebra and Optimizations seminar. I'm glad to welcome Bronevetsky, is it?
Yeah, that's good.
Who just explained that he grew up in Ukraine. That explains his name, I think. Greg's a distinguished fellow. He did his degree at Cornell, and he won a DOE Early Career Award, and then a Presidential Early Career Award. So that's wonderful work, Greg. He came out to the Bay Area to work at Lawrence Livermore and to live in San Francisco.
Yeah.
So, and you've been here about 9 years. Okay, well, it's exciting to get Greg here because the topic he's talking about is rather different from what we normally worry about. We're normally debugging software, but yeah, Greg is worrying about the hardware. So
right.
We're looking forward to hearing Greg. Let me say welcome to whoever's watching on the video. This is such a special talk we're going to record.
Yeah.
Thank you.
Yeah, thank you very much. So I'll start with Go Giants to be, topical. It's very nice. I watch like 3 innings of baseball every 2 years, and they win the World Series. It's fantastic. So I'll begin by actually talking a few slides about just introducing myself, what kind of stuff that I do, because the resilience stuff is, this is a survey, and I cover some stuff that I've done, but it's a fraction of all the different things I do. Fundamentally, what I work on is analyzing what programs do. This could be static analyses of program behavior. So this is automatic synthesis of proofs of things that definitely hold for program executions, and dynamic analysis. So more statistical. You run the program on many times in different hardware, different inputs, and just describe the average variation, that kind of stuff. So on the static analysis work, the whole point is to figure out proofs that a certain property of interest holds. So say, if you dereference a pointer in your code, that it's always, always must be null no matter what the input is. Or you have 2 instructions, prove that they, on every input they access different memory regions, and if so, you can parallelize them, run them in any order or at the same time. Unfortunately, the problem of having one program figure out what another program does is undecidable. So what that means is that all the research in this area is finding creative approximations to what the program actually does. You have things like you model a program by saying, well, originally this thing worked in integers, but I'm going to say it works in numbers that are either even or odd. And you define operations. So originally it did number plus number, so now it's even plus even, or is equal to even, or odd plus odd is equal to even, that kind of stuff. And you take this reduced program, and then you write proofs about that thing, which is now decidable. Now, one thing that I would observe, and this is related now to the kind of work that I do here, is that even though people have done a lot of stuff about pointers and reachability stuff, very little stuff about automatic proofs of mathematical properties, which might actually be really cool, especially since what I am working on is compositional analyses, trying to get multiple analyses that don't really know about each other to work together. This is surprisingly difficult and almost never done because normally, for one analysis to talk to another analysis, they actually have to know about the semantics and variants and APIs that the other guy has. The system I'm working on, they have no idea who they're working with. They can arbitrarily be mixed up. And it becomes really cool to be able to combine domain-specific analyses that understand linear algebra and completely different ones that understand about pointers to matrices, which happen to be linear algebra. On the dynamic side, I'm working on this tool called Sight, which is think of it as a generic way of hoovering up a bunch of information about a program and analyzing it or visualizing it. The simplest variant of what this does is execution logs. So normally you may have a debug log that's a megabyte long. You can't read it. With Scite, you have a way of colorizing it, structuring, so like into the graph structure of the underlying logic. Parallel code, show it in happens before order, so you know what happened compared to what other events. That's just pure unstructured data. If it's structured data, you can do, well, various kinds of analytics. So this is AMG, so Algebraic Multi-Grid, and you can relate the execution time or energy use of AMG compared to the level of the V-cycle that it's currently working with compared to the power cap that you placed in the processor. So combine all these dimensions and see how they all relate. This guy is Lulesh. It's a hydrodynamics benchmark. Here I'm looking at the accuracy of the code using two different measures of accuracy, which actually give you completely different results. As a function of the spatial discretization and whether I'm using float, double, long, double precision. So these are the kinds of analyses that Scite, you could have always done these analyses manually. Scite simply makes them easy, so you can just do a lot of these. So some of the analytics tools that we're trying to build on top of Scite is things like synthesize simple summaries of what the underlying data, so what the underlying program does. So here's an example of we observe the particle tracks of of an actual molecular dynamics simulation and synthesize the potential function that's governing their tracks. So for example, this is Leonard-Jones potential, the real one. And this is the one that we synthesize. The summation we can discuss later, the way we structure our approximations. But we can pretty much pick up on the simple potential functions and just reconstruct them. The neat one is picking up real gravity data from like NASA data sets and recovering Kepler's law of gravity. So not quite Newton's, we haven't gotten that far, but we at least got Kepler. Another example that I'm just finished, this is data from like this morning, is clustering solvers and preconditioners in Trilinos in this case, according to their ability to solve about 850 matrices from the University of Florida collection. So these are the kinds of analyses that, well, I frankly do not understand what I'm seeing here. I just know that there's clear patterns involved. But you guys would actually understand where the data is coming from. So that's the kind of stuff that I'm doing, and afterwards we can discuss these things. But this talk is about resilience. So the motivation for a lot of this work is that, so there's two trends. One, individual transistors are getting smaller and smaller. So when you hear they're getting to what we're now at like 20-something nanometers, and over the next 10 years, by the time we get to, let's say, exascale architectures, it'll be around 10 or smaller. So we're getting much smaller, much denser, a lot less charge for each transistor. And so if there's anything happens, there's a lot less charge to actually upset the current state of the transistor. Also, the gap between transistors is much smaller, so again, you can start having quantum tunneling and a bunch of annoying things like that. On the system scale, they're becoming much larger, more capable. But despite all that, the total amount of power that we can afford to pipe into those things is pretty much capped at 20 watts, at least according to DOE. So that, according to evolutionary estimates of where hardware is going to be in, say, 5-10 years, it's not, 20 megawatts is not possible. So we're going to have to start doing crazy things like not providing as much voltage to these circuits, even though they're very tiny and easy to upset. And these constraints kind of are pressing the possible design options that we're going to be left with. So let me give you an example of the kind of, one of the physical phenomena that can affect, circuits. So what you can see is you have cosmic rays. So protons from supernova, something like this, they hit the atmosphere, and then you get a shower of neutrons and muons, which is like a little picture up there. That's IBM Watson, because it's their paper. And what you get is neutrons, so muons don't count for this thing, but neutrons hit the silicon atom nuclei inside of transistors, break them up, and now you have two charged particles racing their way through a transistor. And they induce electrical fields that kind of separate the positive and negative charges in the transistor and can erroneously sometimes shove some bunch of electrons down the wrong side of the transistor where they were never meant to go. And now you have transistors hooked up into logic gates, hooked up into circuits, hooked up into architectures, running software, and there's a chance that eventually that's going to crash your application, or much worse, make it produce the wrong result without you ever knowing that you got the wrong result. So this is not a certainty that this is ever going to happen. It's a concern. So you have to recognize that you can always make a computer of any size reliable if you spend enough money. I mean, you can say use lower, more reliable transistors. So you have a slower computer, but it's going to be reliable. Take every computation, repeat it multiple times. So like buy 3 supercomputers and have them vote. Or just pump more power. So let's say a megawatt of power is about $1 million a year. Well, increase your power bill. So that this is all just variants of spend more money. This works fine for banks because they have money. Supercomputers, just by being really expensive, it's an unusually poor area. Once we bought the computer, we have no more money left. So, and we're pretty much at the peak of how much money we can afford. So we actually don't know whether in 10, 20 years systems will or will not be reliable. I mean, it really depends on what kind of physics that the material scientists are stuck with and what kind of market motivations Intel, IBM, and whatnot have for building these designs. So there's stories I can tell that tell you resilience will be an issue or not, but bottom line, we don't know. So what this means is that if you're expecting to run algorithms resiliently on hardware that may or may not be reliable, you have to start putting investments into figuring out how to make them reliable. And that's what this talk is about. The key problem that makes this a big challenge is that there is no general solution. I mean, the only solutions that are reasonably possible are those that are specific to individual algorithms. I mean, suppose there was, for any algorithm, you could synthesize a checker for that algorithm that ran asymptotically faster time than the original algorithm. So that would be awesome. But if that were true, then the checker would have a checker, and the checker would run asymptotically faster than the checker. So there would be checker, 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 and it would just keep running faster and faster and faster until the checker had such a tight time bound, it could no longer read the input. And then there's a ton of problems for which you could not check unless you didn't read the entire input, so there's your proof. So what this means is that for each algorithm domain, you have to write specialized solutions, which means it's a lot of work, and work, frankly, has only begun. What I'm going to survey here is a bunch of work that's been done specifically in the linear algebra community. There's been work outside of it, but still the vast majority of algorithms are still not covered. But I'll focus on linear algebra. So the first thing I'll touch is the basic operations, matrix, vector multiplication. And I'll start with simple randomized schemes. So one scheme that you can try is, so you have matrix A, matrix B, you want to multiply them, and the algorithm comes out with a solution C. It claims C is the correct solution. And a simple checker is simply to multiply the alleged solution C and A and B by a random vector R. Note that you're checking cubic time algorithm roughly. We're using three applications of matrix vector multiplication, which is quadratic. So the checker is asymptotically faster than the original algorithm. Now, because it's a random vector and you're simply projecting these matrices onto a random vector, there's a chance that you will not catch the error. So you simply repeat the procedure multiple times for different random vectors, and you simply boost your probability of catching the error if it does exist. And the important thing here is that no matter how reliable your hardware is, there's always a chance it's going to go wrong and produce the wrong answer. We simply want the stuff to boost our probability of success up to today's levels or 10 years ago, but no more than that. Perfection is never really one of our goals. It's just to make it plenty tolerable and reliable for practice, because that's what we're doing right now. Right, and one thing you do have to note is that this is vulnerable to round-off errors. So you're doing A times B is rather different from CR and ABR. So you're doing different operations, and you're going to have round-off. So you cannot look for exact equality. You're looking for equality within a tolerance. And how sensitive a tolerance you choose really is an empirically found value. I don't know of any work for provably choosing it. So that was one approach. Another approach that's kind of neat takes advantage of the property of random self-reducibility. So this property holds for various algorithms, including linear algebra. So think of a single scalar input, scalar output linear function. So you want to find out f of x, right? So what you do is you pick a random delta, and you get f of x minus delta and f of x plus delta. Take those results, take their average, and there's your result. And then obviously keep repeating this until the probability of missing the error is good enough. Now you know that this is a much less efficient check than the last one, which was simply check matrix using three matrix vectors. But the advantage of this technique is that it can also catch bugs in the algorithm. So if for a particular value of x, your algorithm always produces the wrong solution, that's OK. Because you're never going to run f of x on x. You're going to be running it on random other inputs. So even if your implementation is faulty, deterministically faulty, you're sure that even on the faulty inputs, you're going to get, with a high probability, the right solution. And obviously, this works for scalar linear functions, and there's a variant of this for matrix multiplication and other functions. So these are the simple ones, and they have their place. Some of the more powerful techniques come from the error correcting codes area, and I'll spend more time on these techniques. So The idea of this family of techniques, and it has been around for, they even say, yeah, Wong and Abraham in '84, is you encode your matrices. And you encode the matrices in a way that the encoding is preserved by the linear operations you're going to apply in them. So if the matrix is encoded before the operations, the result of the operation is also going to be encoded in the same way, and you can verify that encoding. Right, and this is because this comes from the error-correcting codes community, the kinds of guarantees they have is if the number of erroneous entries in your result is no higher than this number, then we can detect or then we can correct. And obviously you can, if there's a t-bound for how many errors you can detect, the number of corrections has to be less than the number of you can detect. So the basic idea that people have been following for the last 30 years is based on this algorithm. So you have some matrix, and it's going to have some bunch of rows. And what you do is you compute the sum of every row and attach the sum as an extra column to the matrix. So all this is you have the vector of all ones here. You multiply the vector by the matrix and shove the result as the last column. That's all it is. This is the row encoding, so you do this. And you have the same thing for you encode every single column with the corresponding column sums. Obviously, you also have a full encoding where you both encode the rows and the columns. And this new entry over here is simply the sum of the entire matrix. So there's your encoding. Now, suppose you do have a matrix that's encoded in this way. The neat thing is that obviously you can start detecting errors and correcting errors. So let's look at detection. All you have to do is observe that the values here, well, this value is actually the correct sum of all these entries. If this entry right here is incorrect, that means that there's going to be a difference between the sum of the incorrect matrix of this row and the sum right here. So that's how you detect errors. You compare the sum you compute now to the archived sum you computed back on some reliable machine or like way earlier. And same thing for the column. And now, because you've detected an error, but you've also corrected it, because now you know exactly which row and exactly which column, so you know exactly where the error is. Now, once again, I have to remind you, round-off is going to be an issue here. You're not looking at actual equality. You're looking for equality within a tolerance. And the actual choice of tolerance, well, that's completely empirical and, well, depends on the magnitude of the values in the matrix and all that kind of stuff. And of course, there's going to be this tension between detecting false positives, so detecting errors that are just due to round-off, and missing errors that are real. So what I just described for you has been detection. There's also obviously correction. So in order to correct this value, what you have to observe is if you take this thing, and so if you take the sum of all these entries in the corrupted matrix right here, and subtract out the sum right here, which is really just the same entries, but minus but where this value is actually the correct value, the difference is just the difference between the erroneous value at that one entry and the correct value at that one entry. All the other entries in the sum are identical to each other in both the current and the archived sum. So then you have this delta, which is the difference between the erroneous and the correct. Subtract out the delta, now you have the correct value of that entry. This works because you have both a row and a column sum. And then you can detect it and then correct it. Now, what I've just shown you is if you have an encoded matrix, good thing. You can detect, you can correct. The main thing about this particular encoding is that it is preserved invariantly by linear algebra operations. So what you should observe is if I multiply a matrix that's encoded with an extra row and a matrix that's encoded with an extra column, the result is going to be encoded with both a row and a column. And it goes in both directions. So with matrix multiplication, you get a fully encoded matrix here where you can detect and correct at least one error. Mind you, you can correct at least one error, but you can detect at least one error per row or column. So you have a lot of detection and correction capabilities here. It also goes in the other direction. If this is a fully encoded matrix and you factorize it into two factors, then those factors are going to be the row and column encoded. So now you can detect errors. You may not be able to correct them, unfortunately, but at least you can detect errors when you do this encoding. So that's nice. Of course, that's not all you want. Even if you do matrix factorization, go from here to here, you still want to be able to correct some errors in the resulting factors. But the problem, of course, is that these are not fully encoded matrices, so you can only do the correction. So what people have done is they've extended the code. So instead of having regular codes which are just checksums, they also do these weighted checksums. So I'll give you an example right now. Normally, what you would do is have, for this matrix, you have one extra column where you're multiplying A by the vector of all ones. Now we're going to have any number of these vectors. So in this particular encoding that I'll give you right now, you have one vector, which is a vector of all ones. The other vector is going to be just numbers from 1, 2, 3, 4, 5, so just an index. And what you're going to do is add one extra column for every one of these weighted vectors. So that's what it looks like. You're going to have a bunch of original columns, and let's see, one of these entries is going to be erroneous. And you're going to have two checker columns, one with the first vector and one with all ones, and this one has all the numbers 1, 2, 3, 4, 5. So let's look at our error detection, just like I had said before, using both of these extra columns. So OK, if we're verifying against W1, what are we getting? We're going to say we're going to compute the sum in our current vector, the one with the erroneous entry, against the sum that was actually archived, and we're going to get the difference between the erroneous and the archived entry. Cool. If we use W2, you get something very similar, except now you're going to get J, the index of the erroneous number, times this difference. Well, now you can just divide them. You divide A hat, the erroneous A minus original A by the other one, and what you get is J, which is the exact index of the erroneous value. Note that this was a row encoded, they only had row encoding. There was no additional column stuff. But you can still detect and localize exactly what the error is. You can also, and correction is actually easy. Once you can localize, you used exactly the scheme I said before. So if you use the first vector, you're going to get just the difference between the erroneous and the correct A of ij. Subtract that out, done. You have the corrected entry. The trick was that you used a better, more detailed code. You had two columns as opposed to one. Now, these are, what I've been leading to so far is that this is actually a general concept. This is not a single solution that applies specifically to linear algebra. This is an example of error-correcting codes, a very specific one that's very good for linear algebra. So let me just kind of give you a little background on error-correcting codes. So these are just maps from some space of k long words to n long words. So k is your message words, so let's say rows of a matrix. N is the encoded words of a matrix, so these are going to be longer than k. And for us, the language we're going to be talking about is vectors of real numbers, or rational numbers, or fixed precision floating point numbers, something like this. The key idea of error-correcting codes is that within this bigger space of n-long vectors, the truly valid code words are going to be sparse. So there's going to be a big distance between every single valid word. So it takes a lot of corruptions to take one valid word. In fact, let me show you the next slide. It takes a lot of corruptions to go from one valid word to another valid word. In fact, the distance between any two valid words is going to be the central concept of an error-correcting code. It is exactly how many steps do I take from one valid code word until I get to the other code word. So a code with a particular distance, minimum distance dmin can detect errors in less than dmin spots, because when you start from a valid code word, if you take less than dmin hops, you're going to end up in an invalid code word, and that's going to be detected by your code. Further, if you have errors in less than dmin minus 1 divided by 2 spots, that means that you're heading from one of these guys, but not close enough to any other valid code word to make the algorithm confused that you're actually talking about that guy. So if you're going to take anybody in this circle and decode them back to this guy, you're always going to be right. If, however, you have so many corruptions that this code word starts looking like this code word, well, then you're not going to be able to correct it. You're going to assume it's going to be a different code word, and you're going to make a mistake. Know that this is a bit of a misleading visualization, because really we're not talking about two-dimensional vectors. We're talking about n-dimensional vectors. So you're talking about differences in different indices of vectors. So how many of those indices are corrupted? The way that error-correcting codes connect to linear algebra is specifically with linear error-correcting codes, which really are error-correcting codes that are linear spaces. That's all it is. So these codes are defined by generating matrix G, and they're simply, you take a message word, let's say a vector of a row, and then multiply it by G, and you get the encoded messages within this code. There's also going to be a parity check matrix which really defines a null space. So any valid code word multiplied by H is going to be equal to null because it's the null space. The main thing about linear algebra specifically is that the minimum distance between valid code words is determined by the rank of these matrices, specifically the rank of H. So rank of G is literally the number of entries in the non-encoded words. Rank of H is the difference between the length of the fully encoded words and the length of the non-encoded words, which is also the minimum distance of the code. So this determines how many entries can be corrupted and still allow us to detect and correct these errors. So given that this is the real background of that work, and it took people a few years to realize this, the previous scheme with those two code words really is just this matrix. You have the identity matrix for all the regular entries in a given matrix row, and you have these two things for just encoding. So you're going to encode the row with all, the sum and the the running count. And now the main thing is not that this code is that awesome. I mean, it's useful. The main point is that people have done a lot of work on linear error correction codes, and now really you can start picking any code and start deciding which encodings are actually productive for your matrix or for your constraints. So for example, here's a code that replaces the running count with exponentials. The nice thing is that these are powers of 2, and you can implement any operations of powers of 2 using bit shifts. So in hardware implementations, that's a good idea. But then you're going to have gigantic numbers, so maybe it's a bad idea. So your range is going to be limited. One huge thing is, again, numerical stability. In typical linear error correction code literature, you're dealing with binary vectors. So there, you don't worry about, so you're going to be binary linear spaces. If we're talking about fixed precision linear numbers, real numbers, then you have to worry about stable linear encodings. And so Dijong Shen, who worked with Dongarra, came up with some of those. So that is certainly an option, but now we have to figure out what the trade-offs are in that space, which I don't think that much work has been done in that direction. So one thing that Jai Dongarra's group has done actually is using these encodings not for soft error detection, but for hard error detection, so crashes in processors. So they focused on like scale-pack kinds of algorithms where you have, let's say, 100,000 nodes on a blue gene, and then one of those nodes fails. It loses a fraction of your matrix, fraction of your incremental state of your solution, but you still have to go on. So what they do is they have the regular compute nodes, and they have on the side some nodes which only maintain the checksum for the state of these compute nodes. So this might be, let's say, if this is the matrix, the current state of the matrix, this is going to be the sum of all of these vectors on the matrix. And a lot of their work, so it's really twofold. One is the typical decompositions of matrices onto parallel machines are these convoluted things with block cycling encodings, and then these checksums have to account for that. And you have to make sure that your checksums are never stored in the same processors that they're checksumming. So that's going to be a challenge that, that they've dealt with. The other thing is they're not working with just matrix vector or matrix multiplication. They have LU with pivoting and all that kind of stuff. There's a lot of tricks they had to pull to make sure that this encoding is valid at every single step of the algorithm. And if they can't make it valid, they have to duplicate state. I mean, typically they duplicate a small fraction of state, and they encode the vast majority of state like this. But these are the kinds of tricks that those algorithms end up playing. So, okay, before I move on to Sparse, do you guys have any questions about dense encoding-based techniques? Okay. So this works nicely for dense. For Sparse, you have a lot of issues just applying these things. So if you think about the encoding-based techniques, the key idea is you simply add an extra row and column to your matrix, which is extremely cheap for dense linear algebra because you have the matrix is this big square thing, so quadratic storage, an extra row and column, that's linear storage, that's cheap. Sparse, that's no longer true. The number of entries in a given row or column of a sparse matrix is essentially constant. So the amount of storage in a sparse matrix is essentially linear in the dimension size. But now the extra row and column is first, it's linear, which is a problem. And two, it messes up your cache locality because you have this new column which is far away from all the other columns. So then you have to specifically account for this one quirk to make sure your cache locality is still OK. So things have become complicated. Right. So that's why this technique is not typically used. This is something now that I've done myself, trying to extend the other family of checkers, the random-based ones, to apply this to sparse linear algebra. So that's what I'm going to be talking, at least this part is going to be talking about. So as you recall, the very first checker I mentioned for you, what it does is it projects, so you have A and B. Allegedly, here's the result of the multiplication of A and B, and you simply project them both onto some vector Q. And the same thing applies for matrix vector multiplication, factorization. Basically, you take both sides, the input and the output, project it onto a space, compare them. All right. So for sparse, it doesn't work anymore because here you have the checking operations are asymptotically faster than the original operations. But look at MatVec for sparse. So the sparse matrix vector multiplication is linear, it has linear time. But now you're checking it using 3-dot products, which are also linear time. Now, granted, dot products have better memory locality, so it's a lower constant, but you no longer have any asymptotic gains. It really is constant factors. And that's the work that we were trying to do, drive those constant factors as low as possible, lower than just the naive approach. So we focused on not on matrix, but sparse matrix dense vector multiplication, because this is the most common operation in linear algebra. I mean, this is what sparse linear solvers do all the time. Now, so let's recall the problem. So you're checking this identity, which is, it should be the same on both sides. So Q is going to be some arbitrary check vector, which we'll discuss which choices we made. This is the alleged result of the MatVec that the algorithm claims is the true result. And this is a quantity that's going to be computed offline and reused every single time we multiply anything by this matrix. So the goal that we're going to have is choosing a good Q. Now, the traditional Q is the vector of all ones, just like I said at the very beginning for the ABFT technique. Now, intuitively, Qt for this Q, so 1t times A, is really the vector of all of A's column sums. The neat thing is that for many cases, for all the structured partial differences kinds of solutions, these are going to be very structured matrices, right? So they're going to be the column sums of these columns are going to be extremely regular. I mean, look at this. All columns here will have exactly the same sum. Then this thing, and then all this stuff is also going to have exactly the same sum. There's a lot of regularity, which means we can sample. We can take 10% of these columns and pretend that they represent the entire matrix, and then kind of multiply the results by a factor of 10. And if the matrix is highly structured, that's going to be an excellent approximation of the true distribution of column sums, and we're going to be able to catch most errors. And if that doesn't completely work, we can also cluster these columns. So we can have an equal number of representative samples for each cluster of columns, and it can overcome some irregularity in these column sums. But that, of course, doesn't always work. You have plenty of matrices which are not that regular. So we have a couple of other ideas that we threw at the problem. One is conditioning. So if the column sums are not very regular, you can make them regular. I mean, you can make them look regular by multiplying A by Q that is near its null space. So then what happens is that QTA is roughly essentially the zero vector, which essentially means that all of A's column sums effectively look like they're almost identical. Same thing goes for this other conditioning option where you drive it towards a solution which is all ones. But basically the idea is you condition A so that the true variances in its column sums don't matter so much. Of course, now you have to find that vector, which costs you time, and now you have to choose, is it worth the time to find a well-conditioned Q, or are you going to take another option? So the first thing you have to observe is that essentially I just threw a bunch of algorithms at you. So I had the two different kinds of sampling, two different kinds of conditioning. These can be combined, obviously. So the more conditioned the problem is, the more aggressive the sampling can be. And now when you have all these different solutions, they're very different from each other. So what I'm going to show you just how erratic the results are. So this is a metric of how well each one of these individual solvers works in terms of accuracy, detection accuracy. So we measured it using F-score, which is a combination of precision and recall of the technique, which balances your false positives, false negatives, true positives, true negatives. And essentially what we were looking for is the fraction of matrices on which each individual technique could get an F-score of more than 0.9, which is close to 1 is the maximum. And the answer is, well, for some of these things, we could get up to like about 70, 80%. The original dense check, which is Q of all ones, only barely got to 20. And a lot of other techniques, they can be very good for a couple of matrices, but if you toss them at all matrices, they can be quite awful. So the real observation is you have to know which solution technique, which checking technique you want to use for each matrix. So the final technique is throw a machine learning algorithm at it. The one we chose was decision trees because we could then read those things. And essentially what the decision tree found was not surprising, but really useful. I mean, if you have very little reuse in your matrix, then you have to consider, well, then you don't want to use conditioning. So you only want to use conditioning when you keep reusing the matrix a whole lot of times. If you're not going to keep reusing it a bunch of times, don't use them. You should look at, well, the column sum variance. If the column sums are pretty similar, then you want to be doing sampling. If there's a lot of variability, use a dense check and pay the cost of multiplying by the vector of all ones. Now, this decision tree is much bigger than this, but this is the basic idea. And now if you start throwing the decision tree at it, you get much, much better results. Not perfect, and that's important. We're still not at the, we can catch all errors with perfect precision. So blue is the fraction of matrices in which F-score was greater than 0.9. In the original dense check, the very best case option, so using all of our checkers, if you choose the best one for each matrix, you got up to a bit more than 80% of the matrices. We got such a good F-score. And then if you use the model to predict the matrices, we got almost as good, but not quite as good. Mind you, you could get better results if you tried more checkers, but these are the ones that we tried that I just said. If you look at performance, we're getting about 12% error, 12% performance overhead, both in the Oracle model, which is the best, and ours. And if you use the dense check, you get like 25 or so. And you can have a lot of variability. So some matrices are awful in all cases. So that's the basic idea, that if you start combining a bunch of tricks to drive your confidence factors down, you're going to have this issue of, well, you don't know which technique to use for any given matrix, but decision trees or really any classification algorithm can be your friend here and choose the right mechanism for the right matrix. Now, the one last extension is, if you detect an error, what do you do about it? So the one nice thing about matrix vectorial multiplication is that if you know exactly which output entries are corrupted, you can just recompute them. You don't have to recompute the entire result, just recompute those things. So this is a technique to figure out which region of the output vector is actually corrupted. So initially you use one of our techniques. Here I'm using Q is a vector of all ones to check that somewhere in the output there's an error. Where? Well, let's look at the first half. Try Q where the first half is all ones, the second half is all zeros. Well, is it there? No. No, we try where the first half is all zeros, second half is all ones. And keep doing this binary search until we find the correct region. What we found is that it's usually not worth it to find the exact one number that is erroneous. We actually stop several levels shy because there's a cost to doing these MatVecs that's not amortized by finding the exact one entry. So we narrow it down to maybe several entries of the output vector and we compute all those. But the result ends up being pretty effective and much better than simply rerunning MatVec on every error. So questions about this stuff? All right, so I'll move on. The next thing is linear solvers. So now we're getting from individual kernels to roughly the level of real algorithms that somebody might start wanting to use directly. What I'm going to begin is something that I did, which is probably the first work on linear solvers, and you'll notice by far the most primitive. And this is something I'll come back to later. This is a function of a computer scientist doing numerical analysis that is exactly the natural thing to do for early work in the area, but is only now transitioning to mathematicians doing this kind of work. So, I mean, as a computer scientist, the obvious thing for me to do is to shoot a bunch of solvers. This was the Sparselib, Sparselib matrix library and IML linear solver library. So I shot a bunch of these solvers with errors to see what happens. And the answer was about 10% of the time there was a silent data corruption, so it produced the wrong result. But 10% of the time you got a hang, so it just stopped for no apparent reason. And then 10% of the time it aborted just some kind of crash, so segmentation fault or something like this. So to deal with these errors, I tried a bunch of things. So first I tried testing convergence rate of the residual. So residual, in theory, is supposed to come down monotonically. I mean, it doesn't. I mean, error comes down monotonically, but residual oscillates wildly, unfortunately. But looking for oscillations that are so wild that they can only have come from an error. Then various encodings of the data structures, the ABFT thing I mentioned before, as well as a few others. And ways of choosing, how, detection tolerance and the technique you want to be using. So I'll just survey kind of the main findings. So this plot shows you, for any given technique, the overhead of using the technique, as well as the silent data corruption rate that results from using it. The doing nothing approach is right here, has zero overhead, but this silent data corruption rate. And don't worry about these numbers. They completely depend on the error rate, the scale of the system we're dealing with. So think of these as arbitrary units in practice. So what you find, first of all, is if you enable all the standard sanity checks inside of these algorithms, you get some minor overhead and almost no real impact on the silent data corruption rate. If you use the residual convergence checks, you can get maybe half the silent data corruption rate you had originally, but which is not fantastic. I mean, not a huge improvement, but they're not going to cost you a whole lot. So if you want to shove them into an algorithm, it won't hurt you. The most effective things ended up being the encoding-based checks. The thing about them is they're a lot more expensive. I mean, as I mentioned before, you're adding extra rows and columns into rather sparse data structures. So you're blowing up the storage. Now you have to be checking these things. So you're blowing up the computation. So you can get a lot of techniques which are actually very effective. These drive the error rate down by a factor of, I think this guy was already 100. But you're paying like almost 80% overhead. So now, I mean, you at least get this Pareto surface of what the optima are. But now you have to decide what's actually worth your time. And obviously, each matrix, each linear solver is going to have a different Pareto surface. So now you have to have ways of choosing the right point on the continuum. I would argue, so this is essentially the initial work. And the main convenient thing is that you can tune exactly the trade-off between cost and reliability that you actually want. What actually has happened, so this was about 5-6 years ago. What people have done since then, this is the transition between the computer science doing it and mathematicians doing it. So now these are people who are trying to leverage the properties of solvers to improve to improve resilience. I mean, the idea really is that each solver is going to have a bunch of invariants. And it needs them, but they can be corrupted because of soft errors. So the idea is you simply just brute force them to hold every so often. Every so often you check if they hold. If they don't, force them. And that ends up being pretty effective. There have been two approaches by two different groups. The first group from Sandia, this is some of the folks that do the Trilinos library. They leverage flexible GMRes, which is just a two-level scheme. Inner iteration, they use some random solvers effectively as a preconditioner. Then the outer solve, which is the main regular GMRes, it checks whether the inner solver was actually any good, because just numerical breakdown can occur, so it has to check. And if so, it does the standard next step to compute the next iteration. All of these folks did is that allow the inner solver to run unreliably, and the outer loop computes reliably. Outer loop checks in reliable mode, checks the quality of what the inner solver did. Now this thing can be wrong because of a soft error, not just because of numerical breakdown. And then it works out nicely. So it becomes significantly more reliable because you have these two reliability modes. The unreliable mode for like 90% of the computation, and reliable mode for a small fraction of it. What Sao and Vudek did was they essentially did it for they extended the idea. They said, we'll say for steepest descent. So this algorithm assumes that during each iteration k, this invariant holds. Well, that's easy. Every so many iterations, you check whether the invariant holds. If it doesn't, force it. You simply assign rk to be this value, and that's it. And then the thing is, most of the computation outside of this one check and correction is going to be done in completely regular unreliable mode, whatever the manufacturer provides. And then just this check can be done in fully reliable mode, say duplicate all instructions, and it should work out nicely. Note that in this paper, they didn't try the fully unreliable mode, but in principle, that should also be an interesting design point, and they just didn't try it here. The other thing they did was conjugate gradient. So here was a bit more complex. So they observed, so this is the evolution of state in conjugate gradient, and these are the invariants. It holds effectively your vectors p's, and p's have to be adjoint, and these guys have to be orthogonal. And then there's various sufficient conditions for CG to converge. They picked one of the combination of conditions, and they observed that. So this condition can be actually just forced. I mean, just like for steepest descent, this condition can also be just directly forced, assign alpha to just this value. And this condition can be forced by simply setting pk to be rk. So that's what they do. They check if these conditions don't hold. If they do, if they do not, they apply these corrections, and they force the invariance, and then it's supposed to work. Well, this is roughly how well it does. This is two different, so this is a 3D Poisson matrix, so matrix encoding a 3D Poisson finite difference scheme. Error rate is actually fantastically large. It's 4-bit flips for matrix vector multiplication. Note that this is a stress test. This is nothing that unreliable is in the next coming decades is expected to actually hit the floor. Then you have two variants of the problem, actually. But the bottom line is that this is the convergence rate. So you have CG with no errors. In both cases, it's red. Here, it's if you inject errors into CG, but use a restartable CG, where I think you you've restarted search direction every so many iterations. And intuitively, that is a naturally resilient algorithm, but it doesn't work that well. I mean, it does converge, but much, much more slowly than the original CG. And these two are the two techniques. So this is CG with the self-stabilization stuff, and this is FTGMRes that Home and Hiru did. So these guys compared both mechanisms. And you can see it really depends on which mechanism is better for which matrix, as things that usually work. But they are much, much better than doing the naive scheme. They're not nearly as good as simply not having errors. And now this is a valuable trade-off. If you want to spend money on a computer, do you buy a more reliable machine that converges faster, or a less reliable, cheaper machine that maybe has less power needs that converges more slowly? It really depends on the engineering trade-offs. And until we know these trade-offs for the algorithms we use, we don't know what kind of machine to buy. And the thing is, I mean, I'm telling you about the leading edge of the state of the art in linear algebra. It's not a whole lot. It doesn't go into PDEs yet for the most part. So we still have a long way to go to knowing how real applications would fare on potentially unreliable machines. And only after we know that can we know whether we can afford to buy the machines. I mean, maybe they're a low sticker price, but if we can't do any work on them, kind of useless. The last thing I'll cover is something that we did a couple of years ago on Algebraic Multi-Grid. So this is yet another variant of linear algebra that actually turns out to be very resilient to errors. The intuition that you should carry away from this is the point of multi-grid is it's supposed to dampen out high-frequency errors. So it's supposed to go to really coarse systems, so to average across distant regions of a system. So if you have a local error, you can correct it by looking at faraway neighbors. It's supposed to go really fine-grained to do local optimizations. And that's what the V-cycle of AMG does. Turns out that because soft errors are high-frequency errors, AMG is fantastic at them. It actually dampens them out very nicely. So what you're looking at here is the evolution of AMG. So each point so each one of these hops is a full V-cycle. Each one of these iterations is a single coarsening or relaxation step. And what you're seeing here is the error. I think it's the L2 norm, the difference in the current solution vector and the residual vector. And we injected an error in iteration 2, so these errors popped up. And then every single time there's a V-cycle, it just dampens the error. So after a while, it simply is irrelevant. Because AMG is unusually good at exactly the kinds of errors that soft errors are. Now, having said that, what we discovered is that AMG, at least the AMG implemented in Hyper, is full of pointers. I mean, it's a sparse solver. So what happens is it crashes all the time. So all that we actually had to do to make it reliable is actually duplicate the pointers. Unfortunately, you can't duplicate all pointers because then it'll just run extremely slowly. So what we did is figure out which pointers were the most errors in which pointers were most likely to lead to crashes and predicted the top pointers, the ones that were most important according to crashes. And all of this data says is that the more pointers you protect, the more reliability you have, and the more overhead you have, and across different rates of errors and so on. But that's actually an important lesson. You have to pick and choose your plan of attack. Knowing what kinds of errors occur, what kinds of errors are important, really governs what kinds of techniques you want to be applying. In some cases, they're going to be mathematical techniques. In other cases, well, this is just replicating pointers. I mean, technically, we did this manually, but a compiler could have done this bit and really ultimately should. So a separation of concerns is an important point along the way towards doing it properly. Also, control flow errors. That should also be not an application developer's job, but a very good target for a compiler. So before I get to future directions, do you guys have questions about linear solver stuff? All right, yeah?
I was wondering about, you mentioned scalar pack. Did you say it really does have some error correction?
I don't know if it's the production version. They've written a lot of papers. So I'm quite sure you can download the reliable versions. Mind you, these are reliable against crashes of nodes, which today is probably the more dominant error mode. But I don't know if you can I don't know if it's distributed with a standard scalar pack. But yeah, I'm sure they can make it available. Right. So for the future directions, there's a few major challenges. I mean, this is, despite decades of work on this thing, this field is pretty much in its infancy compared to the ton of stuff you have to do before you're actually done. So the first thing is that there really is no general technique. I mean, theoretically, there cannot be a general technique for any arbitrary algorithm. So there's a ton of work on resilience for specific data structures, specific algorithms, like for linear algebra, for sorting, for stacks, queues, that kind of stuff. But they've really targeted solutions, and there's not much in terms of a general theme. And note in this talk, I really relied on linear algebra properties that simply don't hold for most general applications and domains. So obviously, we need more general schemes. There was one work by Joseph Sloan, who's now at UT Dallas, where he converted regular combinatorial algorithms like sorting into linear programming problems. And then those things had iterative solvers that can actually be made reliable, just like linear solvers can be made reliable. The issue, of course, is cost. I mean, you can't just convert any problem into an LP problem and hope for it to be efficient. But this is one way that potentially may lead to a generic solution, although it's very unclear at this point. Another thing that people have tried, Benson is at Stanford, is checking PDEs against variants of different PDE solution schemes. So what you have is one PDE solver that's really stable that's kind of slow, but it's very reliable. That's your stock PDE solver. And you have a bunch of other variants that may not be quite as stable, but are much faster. And for error checking, that's good enough. And now you can check your stable stock scheme, which is slow, against the much faster unstable scheme, for example, and see if there's a difference between them. Then you might signal an error. Similar idea might be have a finely discretized problem and checking it against a coarsely discretized problem. And one thing I'm trying to do is use compiler techniques to see here's an application. I track its definitions, its uses. I train a statistical model on the computation it does. So I don't care what computation it's doing. I'll look at the flow of values. I train a model to predict its flow of values and automatically synthesize an approximator for an arbitrary computation. Now, this work is pretty much at its infancy, but it's another approach that maybe uses statistical modeling to effectively statistically model an arbitrary application, kind of bit by bit, code region by code region. And the one thing I specifically want to emphasize is that this work has mostly been done by computer scientists. And it really, we are the wrong people to be doing this. It's completely reasonable early on because we're the only people who understand that this may be a problem. But right now we're transitioning to a point where computer scientists are taking the tool support side. In fact, I'm hoping to actually do that work. Whereas domain experts and the applied mathematicians can actually do the algorithmic work. And that's the, I think, more appropriate long-term relationship between the different communities. Computer scientists make support tools, and domain experts do specific solutions for specific algorithms. On the topic of support tools, observe that errors are physical phenomena. You have electrons, transistors. You guys cannot think about these things. I mean, I can't think about these things. Or if you elevate the level of abstraction, bit flips in arbitrary instructions. Again, these are not linear algebra concepts. And the thing is, when you abstract away far enough, what you get is actually a lie. I mean, there's Subhashish Mitra from the CS department has done a bunch of studies where he compared high-level error models like bit flip in an arbitrary instruction to low-level error models like bit flips in a given wire or gate. They're vastly different from each other. And it is a lie, but it's a lie that we have no choice but commit because we don't know these real designs. So that's one problem. But the other problem is that even if we knew exactly what error distributions there are, you guys cannot reason about the implications of a neutron on your convergence properties. So a key thing that has to be done is creating high-level error models that actually make sense in the context of an algorithm. So the error in projecting a given vector into a given linear space, or this matrix is, this value is corrupted by multiplying a number by it. That's a numerical concept. It's not a bit flip concept, which is far too low level. Or if you have a list, reordering of two elements in the list. That's a high-level concept. You should be able to reason in terms of those things. And creating these high-level models that are actually accurately approximate the low-level reality is a huge challenge. And something I'm starting to do is use data simulation techniques to say, here's a high-level error model with a bunch of free parameters. Here's the low-level reality. These are both fault injectors that work at different granularities. Tune the free parameters of the high-level model to approximate the behavior of the low-level model. And it's still starting up, so I have some positive results, but there's still a ton of work to go. The final thing is that we have this is also completely tool support. We don't really have resilience-aware programming models. I mean, you think of any code that's longer than 10 lines of, they're just 10 lines, adding resilience to it is a bear. I mean, are you really going to take every single expression and statement and put a checking expression right after that? It's just not a feasible programming model. And there really has not been much work in adding resilience mechanisms to applications of any real size. So Matana Rez at UT Austin has been doing this with containment domains where you decompose the code into these hierarchical domains where you have localized recovery. But there's still a whole lot of work to go. I mean, think of how easy it is to program parallel machines. I mean, this is like 30 years of work on programming models, and they're still obnoxious to program. Resilience is harder, because with parallel programming, you have two instructions and arbitrary interleavings between them, so arbitrary orders. So that's hard. That's been decades, and we're still not even close to solving it. Resilience is not arbitrary orders, different instruction. Originally it was this instruction. Now it does something completely random because of an error. Program to that. We are decades behind in making programming models to deal with this kind of abstraction, but we're coming up with machines where this is really going to be a challenge. So we don't know what to do. We don't know how to empower developers to actually deal with this. But we really need to be there, so that's the kind of work that should be done, but still in its infancy. So those are the challenges. Thank you, and I appreciate any questions or comments.
Thank you very much. Great. Good timing. Has anyone got a cure?
I have a question. Maybe this is too big of a question, but early on you said these systems don't exist. Do you have models for the types of errors you think might exist?
Right.
But do you know anything about what happens today in the supercomputers you deal with, or?
So it's a problem. We know, okay, so there's a bunch of partial evidence. So you can have corrected errors in memory because you have error correcting codes on regular memory, so we know how many got corrected. How many were missed? Or I mean, also detected. We have those errors as well. Those typically lead to no crashes, but at least we know how many of those exist. But how many were missed is unknown. But those are the easy ones. They are checking the identity function, right? Because it's just communication. If you're checking if there's an errors in the computation, which there are no good checks for the complexity argument, as I said before, there's just nothing. So we don't know how unreliable those things are. So what we have to go on is what Intel is guessing, but now it goes to their marketing department. I mean, you talk to their engineers, they have reasons to be worried, reasons to not be worried, and different people say different things, which is a problem. I'm actually on a proposal right now where at least we'll go on an open source model and say, if errors happen in the circuit design of this thing, how would they propagate? Hopefully, we might parameterize it to a Intel processor or an IBM, because we have those as partners. Or they may use our stuff to apply to their designs and not tell us exactly what they did, because it's secret. So it's tricky. It's about all I can say. But no, I will say one more thing. People do shove processors into neutron beams, and you get the data from that. The issue there, besides the cost, is it's never going to be my application. And we don't have ways of generalizing what happened to one application to what's going to happen to my application. So, yeah.
I wonder if some of these tools and ideas, especially for particular fields, can be applied to solve the big old problem, not the future problem of debugging.
Okay. I mean, can this be used for debugging?
Sparse algorithm pass all the compiler things. And
Yeah.
maybe even given numbers which are credible. But
Yeah.
there's no way to make sure.
Okay, yeah. So there's a few things you can do, obviously. One thing is the idea you run the algorithm at a coarse grid, fine grid. They should be roughly similar, and the spots where they're different are going to be shocks. It's interesting to know where they are different. So you can use some of these resilience techniques to check for that kind of stuff. The idea of random self-reducibility, this guy, let's see, this guy right here. It's exactly for bugs. Actually, if you remember, like in 1990, there was a bug in the Pentium processor design. That's kind of where that paper came out of, where they said, f of x is erroneous in some inputs, so I'm never going to I'm going to switch f of x. I'm no longer going to run an f of x. I'm going to run on random instances that are similar to x and interpolate, right? So even if there's a deterministic bug, I'm not going to hit it deterministically. I'm going to hit it stochastically. A lot of my work, and this is actually, I think, much more open. So the system, the site system, is exactly for debugging. Actually, what I'm showing you right now is me debugging my own codes. My codes were, compiler analyses in that case, were so obnoxious I could not debug it, so I had these giant logs. So now imagine if you've exposed some of your state to a tool, can this tool help you explain what your program is doing? The dumbest variant is simply it shows you your entire log in a way that's readable, but it's just a log. Fancier things would be things like this, where it says that here is an automaton. I don't know what you actually implemented, but what it actually behaves like is this automaton. Is this what you meant to write? That might be informative. Things like this may be cool because it says, you coded up Leonard Jones, and I found something insanely different. There's got to be some bug between, in your code that makes it not be what you thought, what you thought you implemented. So maybe these techniques, synthesizing automata, synthesizing formulas, may be a good debugging clue. They can be used for resilience because now I can use, this is what you implemented, and then this is what I found. I can use this to check this. So they're certainly related. People have not really pushed on it very much, and they really should. In fact, I'm planning to.
Greg, I could mention that some of us write and solve, say, for symmetric system, iterative solvers, and to test if the matrix vector routine looks like it represents a symmetric matrix. We can use a few matrix vector products to test for symmetry.
Okay, so that's good, because then if you were assuming symmetry, you can at least verify it, yeah, cheaply.
And the same, some solvers need products with A and also with A transpose.
Right.
So a few products can test if it looks like it's the same A that you're multiplying by when you do the transpose.
Right.
So it's testing the user's software, but I was interested to see you using products to test the hardware.
That's right, yeah. And there are general techniques, and you can use, let's say, randomization, making sure that what should be the same is in fact the same.
Yeah, random vectors.
In fact, one thing that this is related to is type systems, because think of what, like, integer, classes, like, what do? They demand that the programmers say twice what they meant to do. Here's your source code, and here are the types you assigned to the source code, and now the compiler can say that the stuff you said twice was in fact the same. You said the same thing differently, were they in fact the same? You can imagine this stuff being analogous. You say, here's my main algorithm, here's another description of what my main algorithm was supposed to be, like these things are supposed to be the same when projected onto this space. And now some other system, a dynamic checker or a static checker, can verify that you said it twice, you said the same thing twice. This may actually be a general technique for, again, static dynamic checking for correctness of your software and correctness of your hardware.
Well, it's good to know that as machines get faster and
Yeah.
faster, there's someone worrying about them tripping up.
Yeah. Yeah, there's a lot of people worrying, and there's just too many layers to think about. It goes from materials all the way up to applications, and that's a huge challenge. When it's a multi-layer problem, nobody understands the whole problem.
Circuit design people have to worry a lot already.
Yeah, exactly.
Okay, well, I want to thank everyone just for coming, but especially it was our colleagues in Berkeley who asked us, could we have this talk in real time? And in the end, we couldn't manage that, but at least we do have a recording of it. So thanks for that good question to our colleagues in Berkeley. So let's thank you again, Greg.
Thank you very much.
Happy Halloween, everyone.